Hello everyone. In this video we are going to look at the response of a mass spring damper system, but not the regular one that you always see. We're going to look at the case when the spring is nonlinear. Because many times in your courses you have seen this mass spring system. It could or could not have a damper, right? So you can or cannot have this damper. And the spring, the force of this spring was simply negative k times x, where x is the deflection and k the spring constant. Now in reality, none of the springs that we know is perfectly linear for all range of x. If the deflections in the spring are small, then we can approximate it by this linear function, but in reality, most of the time there is a nonlinear terms as well, and the force versus displacement graph is not going to be a straight line. Many times you see a cubic term added. Okay, so if you plot the spring force versus deflection, you either get this red curve, right, with this kind of curvature, or you get this blue curve with this kind of curvature. Where in this blue curve, which we call it hardening spring, this constant alpha that you have is what? It's just the constant itself is positive. So the force keeps going up like that. So in this case, the magnitude of F, this is the magnitude really. The magnitude F is some K times X plus some alpha, positive alpha times X cubed. And in this case, the alpha is negative. It's the same function, but alpha is negative. And the explanation of that is outside the scope of this lecture. It goes back to strain hardening or other effects, the nonlinearities in the material. So it's a material science lecture really, which as I said is beyond the scope of this video. But in reality, you always have nonlinear terms. And this alpha might not be as big as k, sometimes b, but in general, the question is, if I bring this extra nonlinear term, what's going to happen? A lot of things. Let's take a look at what. So let's say we look at the mass spring system first. Let's say there is no damping, and the spring is nonlinear, and there is no external force. Okay, so no damping, no external force. And this is the governing equation that you will get. Mx double dot plus kx plus alpha x cubed equals 0, right? So what kind of response do we get out of this system? Well, the first thing you'll see that, unlike the linear case where the period t of the oscillation is basically 2 pi over omega, right? And omega is a constant number. It's simply square root of k over m. So that was constant, and it does not depend on the initial condition that you start, okay, or the amplitude of the oscillation. It does not. This t, if you plot it versus x0, let's say x0 is not 0, but x dot 0 is 0. So you just started from some non-zero x0. Again, x dot of 0, let's say it's 0. If you plot the amplitude of the oscillation, the response, so this x equals some a, in this case, times cosine of omega nt, right? It is going to be constant, this amplitude versus x0, or the period of oscillations in this case, right? Based on this x0, this is t, not a. This t is not going to change, because in this case, a is going to be the same as x naught. Okay, but in the nonlinear case, it does. So here, you can see some plots. This is t versus x0 or a. And this is when it is hardening spring, alpha is positive. You see the period starts dropping. Why? Because as you move forward, k is getting bigger and bigger, right? The equivalent k equivalent, right? So if you divide the force at any point by the displacement and call that ratio equivalent, you see this k equivalent is getting bigger and bigger, and you know when k gets bigger, omega gets bigger, so t should drop, and that's what you can see over here. But here, when alpha is the softening, K equivalent goes down from a linear scenario, right? So here you can see, if you look at this blue curve, if I'm here and I divide these two numbers, this K equivalent in blue is less than the green curve. So this guy goes down, so T goes up, and you can see that behavior here. So the period of oscillation does depend on the sign of alpha, and it does depend on what? On the amplitude of the oscillation. Okay, and here I have generated that graph for you in MATLAB. So here is my MATLAB code. I use this set of numbers. You see, I set my F0 and omega, which are the basically the frequency of the excitation and the magnitude of excitation to 0, and the damping C to 0. So I only have M, K, and alpha. I simulate it for 30 seconds and for different initial conditions from 0.2 to 1.2. And I generate the plot one time with positive alpha, the other time with what? As you can see, with the negative of the same alpha. Okay, so if we go ahead and run this section, you see those two plots will be generated for you. Okay, there we go. So if I stretch this so you can see it better, you see that the period of the oscillation is not constant. Okay, that's the first thing. Now, is that it? No, there is a lot more to it. One thing before we go and talk about the next part, which we add damping and excitation, is you need to be careful when simulating the system for negative alpha. Why? Because the spring force, which is basically this, since alpha is negative, so practically this is like negative kx plus magnitude alpha times x cubed. And if, let's say for instance, this k is 2 and this alpha is 1 or negative 1, so you get negative 2x plus x cubed. The problem is this. If this x becomes bigger than what in this case? It becomes bigger than 2, or not 2 actually, bigger than square root of 2 in this case. If x becomes bigger than square root of 2, then this spring force is going to become positive, which means the spring is helping your system to vibrate. And that is not what the spring does. The job of a spring is to oppose vibrations. And so instead of being like a real spring, it is going to be the opposite of what the spring does, or we call it what? We call it negative stiffness. So instead of this magnitude K equivalent being a positive number, what happens? This K becomes a what? A negative. So like a spring is helping your system to vibrate, and then you see this amplitude of oscillations. These guys, if you do the MATLAB using OD45 that I'm doing, right? So here for a set of numbers, I get the response. And then here I have this utility function that I pass to it my time values and my signal value Z1, right? Which is the same as X, and it gives me period. The problem is this signal here is going to have very huge oscillations, very huge magnitudes of oscillation. So the system becomes unstable. Okay, and so you're not going to get good numbers out of that because this guy is not going to oscillate really. So you need to make sure that you only allow it for so much of displacement, as long as in this case, let's say below a square root 2, right? When you pick your initial conditions, you need to make sure this guy is what? Below a square root 2. Otherwise, for this negative alpha, you're going to get an unstable system. So just keep that in mind, and this term negative stiffness, just keep it in mind. So here is my code, as I said, and the utility function here that I wrote, there are two of them. One is the function for OD45, which implement the equation. You see here z.1 is z1 is the same as x, z2 is the same as x dot. So you see Z1 dot equals Z2, Z2 dot equals negative KZ1, negative alpha Z1 cubed, negative CZ2 plus F sine omega t divided by M. And F in this case, I set it to 0, C I set it to 0. And this is the function utility for finding the period. So it goes through the signal and it looks at all the places where the value of the signal at each point times the next point of the signal is negative, which means you are crossing a 0. And if you do, then the time value for that location is going to be stored in the zeros of the function. And then you subtract the third 0 from the first one. And you might say, why third one from first one, not second one? Because the second time you are not what? You're not going to show the oscillation, right? So if you start like this, right, and this is your X signal, and this is your T. So here is your first location of 0, here is the second one, here is the third one. If I subtract second one minus first one is half of the period. So I subtract third one from first one, which is what? Which is one entire period of the function. Okay, so that is what my utility does. And for it to be accurate, you need to make sure this X and T have a lot of values in them, or the sample time is small. That's why you see here, I'm using what? I'm using a very small time point. So the accuracy of the zeros are good. Okay, if you use 0.1 or some big step size, that is not going to be accurate. So that is the first part. Now let's go and talk about some other effects other than this variable period. So here we're going to add the external excitation harmonic as well as damper, a linear damper. And if you do that, this total equation, by the way, is called Duffing equation, the name of the person who first studied it. And in this case, since there is this excitation, we call it force Duffing equation. So if this guy is not there, we just call it Duffing equation. With this F added, F sine omega t, we call it force Duffing equation. So what kind of response am I going to get from mass spring damper, nonlinear damper with external excitation, or a Duffing equation? Well, that is quite a bit interesting. One thing I will get is, although my system has only 1 degree of freedom, x, when I look at the frequency response of the system, instead of having one single peak, it is going to show you several peaks. Remember, if the system was linear, if you remember from linear vibrations, if the system is linear, so this term is not there, then the frequency response of the system is going to be like this, right? You only have one peak here at this omega frequency, right? And which, if I'm not mistaken, that would have been omega n times square root of 1 minus 2 zeta squared. And this is your peak M value. Okay, so you only have one peak when there is damping. If there is no damping, then it is going to go like this. So you are going to, it is going to go like that. You're going to have an asymptote here at omega equal omega n. And you're going to have infinitely big oscillations, which we call resonance, right? Of course, even in this case, we still call it resonance, but that's what happens when zeta equals 0 and this omega peak, omega r equals omega n, right? So you only have one peak in the system. And if there is no damping, what happens? As I said, the magnitude of this MR goes to what? Goes to infinity. Now, in the case of this nonlinear system, what happens? First of all, you don't have only one peak, you have several peaks here. So here I have simulated the system for values of M, F, K, and omega. Omega of the excitation equal 1, alpha is 0.75, and C is 0.02. And the system, although it looks like a simple harmonic, this is in the steady state, right? So this is X of steady state. Because you see, I simulated it from 0 to 500 seconds, but I'm only showing you the last 10% of the time where the signal is stable. And you see that it looks like there is only one kind of frequency in the system, but it's not. There is one major frequency that you can see, but if you look at these peaks, they are not all the same. So there are some basically smaller components of frequency that you don't see with higher frequency. But if you apply FFT, right, if you look at the magnitude of FFT in this signal versus frequency, you see that not only I have this major frequency, which you can see, I also, at higher frequencies, I have one peak here and I have one peak here. So you see multiple peaks. This kind of behavior you see in systems with multiple degrees of freedom if they are linear. So just like the example I showed you previously, remember in my previous video on Riley, if I look at this system, right, where it has 2 degrees of freedom, and if I come and excite these with some harmonic function, right, some like f sine omega t or something, in this system, and let's add some damping so the system does not go to infinite at infinite values at omega equal omega n. In this system, if I look at the frequency response, you'll get what? You'll get, so if A is the response, right? A is the magnitude of x1 or x2 or the vector, and this is this omega, you're going to get 2 peaks. One is at omega equal omega 1, the other one is at omega equal omega 2, right? Since system has 2 natural frequencies, so you're going to get 2 peaks. But in our system, which only has 1 degree of freedom, having more than 1 peak is interesting in the frequency response, and that's what it does. And these are because of the nonlinearities. Okay, so you're going to see this kind of response. So in general, the MST system with nonlinear spring, the response of it, the frequency response of it is different. First of all, you might have several different amplitudes of frequency response for 1 omega, and that's exactly what you can see here. For one single omega, you're going to have 3 peaks or several peaks in general. The other one that is even more interesting is the amplitudes of all of these peaks stay finite even if there is no damping. So even if I kill this damping and set it equal to 0, no damping in the system, still none of these peaks will become infinite. You will never get infinitely big responses like this picture that I just drew for you, this red scenario here. It will never happen. You always get limited, finite responses, even if your omega here is equal to what? Let's say this omega of u is equal to square root k over m, which is the natural frequency of the linear system, or any other frequency for that matter. Doesn't matter, just change it from any to any and set the damping to 0. You will never get infinite peaks. So now linear systems will not have infinite peaks, and they might have several. Good. One more thing that is interesting is because we have several peaks at the same frequency, and you might have several basically harmonics under one single response, when you change this omega, then if you plot basically the frequency response or the amplitude versus frequency, then, as I said, for a linear system, you'll get 1 peak. Now, because here you have several peaks per omega, that means you can jump. Because now, at this moment, with this omega, you had some peak, some frequency response. Then, look here. You see, this is my omega. Per this omega, I have 1 peak here, I have 1 peak here, and I have 1 peak there. You see? You have 3 peaks per what? Per omega. And because of that, you can have jumps. So your peak jumps from here to what? Here. And especially when you change omega, that is even more interesting. And it is different, this behavior, if you plot this frequency response, right, this one, by recording the peaks per this omega and then change this omega, right, change this input frequency. And you're going to see that here, while I was there at this peak, when I change my omega, because you can clearly see it, this is your omega, right? When I go from this frequency to this one, now my peak jump from this to what? To this. I have a jump. And when I go forward from this frequency to this frequency, again, I have what? I have another jump. So depending on what frequency I pass to the system, I get different what? Different amplitudes, and so I get what? This different jumping from this one right to this one, right to the point above it. And the way they change, for alpha of negative, the peaks will have this kind of behavior, as you can see. For the positive one, they have this kind of behavior. In other words, the direction of the curvature is different for them for different frequencies. So you have the jump phenomenon, and that is because you have several peaks. The last thing I want to talk about is chaotic response. Yes, this system can be chaotic too. It can be extremely sensitive to initial conditions. Here is one such response where I set m and omega and alpha equal to 1, k of 5, c of 0.2, and f of 10. And the behavior of the system is not going to repeat itself. And if you look at the phase space, you're going to see this kind of infinity shape response, and it will never settle on one single periodic curve. Okay, so you see that if you cut basically this state space trajectory, so if you plot this state space trajectory versus time, so this is x and this is x dot. If you plot this versus time, right? This one we call point car map, and I'll talk about it later. But if you plot this point that you started, after some time, it hits a point that is not exactly the same as that original point. Okay, and after another similar time, so if you call this time from here to here t, whatever it is, and here again from here to here another t, and get these intersections from this trajectory, again, when this one comes here, it is going to hit at a point that is different from those two original ones. So it never goes back to itself. It never becomes a closed curve, and so it never becomes perfectly harmonic. Now, the last interesting thing I want to show you is here, you can see the Duffing equation. We just changed this in this picture. Not I did, but the author changed this sign that I had with cosine, right? So here I have sine, but you can have it cosine. And this B called it F and removed the linear term. So this K is the same as C for me. I don't have a K here in this equation. This K is set to be equal to 0, so you only have the nonlinear term. And this B, as I said, for me is F, and this cosine is sine. And this is for an omega equal 1, basically. So it's a simple equation, simply a special version of the Duffing equation. And the author of this paper, which is Ueda, in 1991, in this paper called Survey of Regular and Chaotic Phenomena in Forced Duffing Oscillator, he found that based on the value of K, which for us is called alpha, right? Based on this alpha, and B, which is the magnitude of the harmonic response, excitation F, based on the values of F and alpha, you have different regions that the response, like here where it's white, it is periodic, right? So if you see a region that is not hatched, that region is what? That region is periodic. If you see a region that is completely hatched like that, that is chaotic, like this region here, as you can see. And if you see a region that is dashed lines instead of solid lines used for hatching, like these areas, then it's even more interesting because you can have chaos as well as periodic at the same time. So it's called chaos plus periodic is coexisting behavior. So if you look at the state space of the system, you basically see this kind of behavior like this, which is not going to settle, right? But in the middle of that, you're going to also see, let me use a different color, you're going to also see a closed curve like this. So it's a combination of chaos and what? And periodic. You call it coexisting behavior. That is one of the kind of weirdest thing you can see in this nonlinear system. So yes, a simple nonlinear spring is going to change the behavior of the system entirely and make lots of new interesting phenomena. So this picture here in this video is borrowed from Ueda, and this other graph here, this one, is which is frequency response for alpha positive and negative. It is borrowed from the book Nonlinear Oscillations by Naife and Mook. Okay, so the credit goes to these people, and hopefully this video was useful to you. So I'll see you in the next lecture. Thank you.